Let me give you an idea of how vast space is. Voyager 1 has been flying for 46 years. In all those years, it has crossed about 1/390th of a single light year. At this rate, the nearest star is roughly 75,000 years away. So how can we send people to another star? The only way we can, using our current understanding of physics, chemistry, and space-time, is to use a vessel where the crew that arrives isn't the crew that left. Children born in transit, grandchildren, great-grandchildren stepping out onto a new world. That's a generation ship.
Let's start with the smallest question. How few people can you seal inside a tin can for centuries without the gene pool collapsing? Researchers have argued about this number for 25 years. Their answers vary by a factor of 100. In 2003, anthropologist John Moore ran demographic models on historical migrant bands. His conclusion: 150 to 180 people could survive 8 generations if couples delayed having children until their mid-30s and accepted arranged pairing rules. That's the lowest theoretical limit, 80 people. Cameron Smith at Portland State disagreed hard. In 2014, he looked at minimum viable populations for wild species and saw a number dangerously close to the genetic bottleneck humans barely survived 70,000 years ago. His floor was 10,000, a small city in flight. Then Frederick Marine and Camille Belufi built Heritage, software that simulates every birth, every death, every miscarriage, every pairing across a 6,300-year voyage to Proxima Centauri. Their headline result: 98 settlers, strict no consanguinity rules, 100% success rate. 98 versus 10,000 versus 40,000. This difference in numbers isn't disagreement exactly. It's different bets. Small numbers assume nothing goes badly wrong. Large numbers assume some generations will be terrible. An epidemic, a hull breach, a civil war, and you need a buffer for catastrophe. The current best synthesis from Andreas Hein and colleagues settles around 500 to 10,000 for a robust mission. Project Hyperion, the interstellar design competition whose winners were announced last July, split the difference. Their brief specified 1,000 people, give or take 500. But the crew puzzle isn't the hardest part of this. The hardest part is what happens when you seal those 1,000 people inside a closed ecosystem for 250 years. Fortunately, we have data on this exact scenario because someone ran the experiment. Unfortunately, it went badly. In 1991, 8 people sealed themselves inside a 200,000 cubic meter glass dome in the Arizona desert. 7 biomes: rainforest, ocean, savanna, marsh, desert, farmland, habitat. The plan: prove humans could live indefinitely inside a closed ecosystem. They stayed for 2 years, but almost nothing went as designed. Within 16 months, oxygen had dropped from 20.9% to 14.5%. The crew was breathing air as thin as 4,000 meters altitude. Soil microbes were eating oxygen faster than plants could make it. They had to pump fresh air in from outside. The closure had failed. Of 25 small vertebrate species introduced, 19 went extinct. Every pollinating insect died. The crew hand-pollinated their crops. Ants, cockroaches, and katydids took over. The carefully designed 7-biome ecosystem had collapsed into a much simpler, weirder thing nobody had planned. The crew lost an average of 16% of their body weight from chronic hunger. They split into 2 warring factions inside the first year. 8 people, 1 greenhouse, 2 years. A generation ship would need to do all of this without the resupply truck for 250. The lesson isn't that closed ecosystems are impossible. It's that they need massive redundancy, simpler food chains, and probably no soil at all. Real designs use hydroponic stacks under LED light. Algae bioreactors handle most of the oxygen budget. The plants you see are mostly decoration.
The animal manifest looks nothing like a farm. Bees for pollination. Black soldier fly larvae for protein, with a feed conversion ratio of 1.3 to 1. Tilapia in aquaponics tanks. Quail for eggs. Maybe rabbits for meat. Cows and pigs are too inefficient by an order of magnitude.
Now, the ship itself. To fake gravity, you spin it. Centripetal force equals angular velocity squared times radius. Spin too fast, and the inner ear rebels. Nausea, vertigo, dizziness on every head turn. To stay below 2 rotations per minute, you need a radius of at least 224 meters. That's the floor. The ceiling is Gerard O'Neill's cylinder. 8 kilometers across, 32 long. Hundreds of square kilometers of land curling around the inside. Or last July's Hyperion winner, an Italian design called Chrysalis, a 58-kilometer modular cylinder built to carry 2,400 people.
Living quarters sit on the outer hull, where gravity is full. 5 meters of water overhead, doubling as radiation shielding. Hydroponics and aquaponics on the mid-decks. Command and recreation at the low-gravity core. The engines sit kilometers behind everything to keep neutron radiation away from the children. Now, how do you actually move all of this? Antimatter is science fiction. Warp drives are science fiction. Wormholes are science fiction. What's left is a short list of real engineering papers. The most famous one involves dropping atomic bombs out the back of the ship. Project Orion, 1958. Freeman Dyson and Ted Taylor at General Atomics. The idea: detonate fission or fusion charges against a giant pusher plate cushioned by huge shock absorbers. With deuterium fusion bombs, Dyson calculated you could reach 3 to 10% the speed of light. Orion was 1960s technology. We could have built it. The 1963 Partial Test Ban Treaty killed it. You cannot legally launch a vessel that detonates nuclear weapons in Earth's atmosphere. Dyson himself noted that even the fast version would only let the grandchildren of the original crew reach Alpha Centauri. The successors are fusion pulse designs. Project Daedalus in the 1970s, 12% the speed of light, but uncrewed and unable to slow down. Project Icarus started in 2009, aiming at 5% crewed. The honest ceiling for a people-carrying ship is 1 to 10% C. At those speeds, only a handful of stars are reachable. Proxima Centauri at 4.2 light-years, Alpha Centauri, Barnard Star, maybe TRAPPIST-1, 40 light-years out, if you're willing to budget 800 years and 32 generations. Anything farther is geological time, not human time. And then comes the twist that's haunted this field since 2006. Andrew Kennedy ran the math on a simple question. If propulsion technology keeps improving, when is the best time to leave? His answer for Barnard Star, assuming modest annual improvement, was startling. Don't go until the year 2718. The reason? If you leave today at 0.5% the speed of light, a ship launched 2 centuries later at 5% simply overtakes you. There's a 1944 science fiction story called Far Centaurus, where exactly this happens. The generation ship arrives. Humans are already there. But Kennedy's curve has a minimum. Ships launched at the right moment never get overtaken by anyone. You can mathematically optimize the departure date for a starship. The optimal year depends on how fast you think we'll keep getting better. Today is almost certainly too early. Or you skip the human crew entirely. Ship cryopreserved embryos, artificial wombs, AI nannies to raise the first generation on arrival. Ship mass drops by 3 orders of magnitude. The crew size problem disappears. The biosphere problem disappears. The ethical problems multiply. Nobody knows how you raise children without parents.
The Hyperion competition's winning design isn't science fiction. It's a buildable blueprint with a date on it, sometime after the year 2300. The question isn't whether we could build a generation ship. The question is whether we'd still be the same species at the other end.